Thank you very much. I'll present some of the results we have recently published in this Journal of Fluid Mechanics paper, appeared a few months ago. So for details as well as for many citations that are needed, that please don't hesitate to look at that paper. And now I go to my presentation. So HVBK, two-fluid model, not three-fluid, two-fluid for quantum turbulence, and we have some tests on energy cascade and higher-order statistics. So the higher-order statistics are described, as I have mentioned, in that Journal of Fluid Mechanics paper. It is a work performed in collaboration with Zhentong Zhang. He's 2 years postdoc in Rouen. Emmanuel, who already presented the model and some of the results, Ionut and myself, and some of the results are ongoing work on the relationship between second to third order moments with Juan Polanco and Mikhail Gauding. We have been using his DNS code. So the laboratories are Laboratory of Mathematics in University of Rouen, Laboratory of Fluid Mechanics and Acoustics in École Centrale de Lyon, and my laboratory is Continental and Coastal Morphodynamics in Rouen. The outline of my presentation is I will rapidly describe the HVBK two-fluid model, and I will go to some results. Some turbulence statistics focus on the mutual friction force as a result of the DNS simulations. And then the scale-by-scale energy budget, so that is the relation between second order to the third order moments. And we'll probe with a particular viewpoint the internal intermittency, because we look at the transport equation for the third order moments that will be related to the fourth order moment. And that normalized appropriately allows us to look at what we call flatness, in some other communities kurtosis, and it is one simplest way to probe the internal intermittency. We look at that over the relatively large scales. We do not have an inertial range. We have what we call a restricted scaling range, but we also look at the intermittency at the smallest scales that we resolve. So that will be reflected by the flatness of the velocity derivative, so the smallest scales, the small scale intermittency. No need to describe the model because it had already been presented. So the helium-2 fluid model, so there's some large scale averages for what happens at the quantum level. The total density is the sum of the densities of the normal fluid and of the superfluid. For temperature larger than T lambda, we have mostly a normal fluid, and below T lambda we have most superfluid. This does not work. And so we'll vary the ratio between the normal fluid and the superfluid between a ratio of 10 above T lambda. A little bit below we have equal part of normal fluid and superfluid, and below T lambda we'll have most of the fluid will be superfluid and a little bit of a normal fluid. A lot of discussions on the exact expression of the mutual friction force. So at the end we stay at the simplest form that Emmanuel presented just before. We had a lot of questions from two of the referees, why do we choose this and that. So one large appendix of our paper is devoted to the choice of the exact form of the mutual friction force. And we emphasize that with taking into account the tension, for instance, etc., that does not change the results that we obtain here, but it might probably change some other results. But at least for what we look at, that is not so important. The governing equations are like that, so incompressibility for the normal fluid, for the superfluid, and Navier-Stokes like transport equations for the normal fluid and the superfluid with the expression of the mutual friction force. Note the opposite sign here that will be translated into the fact that momentum, energy, and some cascade will be enhanced for the normal fluid, and the opposite will happen for the superfluid. A lot of literature, again, the previous two presentations and some other before that, there are some debate. Some people agree with this, some other people agree with that, with different, with the basis of more or less the same model, but with numerical simulations that may be a little bit different. So we are in this family of models in which the ratio of the viscosity of the superfluid that is chosen, so the energy is not, it flows to the small scales, even if the viscosity of the superfluid will be much smaller than the viscosity of the normal fluid that is in charge to dissipate. The results I will show today, this ratio is equal to 0.1. But again, in one of the appendices of our paper, we reduced that by a factor of 4, and we showed that the results were not qualitatively different from that. So different ratios of the viscosities. But it is something that is constant with the temperature, whereas some other gradually damped HVBK models, they consider this ratio a variable with the temperature. So some references are mentioned here, but as I have said earlier, in the full paper you have all papers that we are aware of. And here some of the people that worked with this kind of truncated HVBK model, so that ratio of the viscosity constant. Some common observation of all previous studies for the HVBK model, that everybody sees over a more or less wide range of scales, k to the minus 5/3 for large scales or intermediate wave numbers. We see some locking between the normal fluid and the superfluid, and it is what we'll also show for some of the results. And of course, the scaling of the structure functions was studied by many people, most of them with the use of ESS, extended self-similarity, because most likely at those values of the Reynolds number, we do not really have something that will be called a scaling range. So the exponent gamma or zeta, whatever the name, it cannot be computed properly. So we do that through the help of the third order structure function, so that comes to the ESS model. And intermittency for the superfluid turbulence was studied through this scaling laws, scaling range, and scaling exponents. But also, as we show, it can be studied for the very small scales. So we see how the flatness of the derivative will increase for different parameters, so in particular for increasing Reynolds number. Some incompatibilities of these studies, so some references show that the Kolmogorov scales, again, as they had been computed from those simulations that increase or decrease with the temperature, so there's not a real an agreement between all studies. An enhancement of turbulence intermittency, so some people agree, some people do not, and depletion of intermittency. So things are not really clear, so we wanted to, this is one of the reasons we went to the simplest model that we had for the coupling between these two fluids, so HVBK 2 fluids models. It is not a 3 fluid. And we take a particular look at the role played by the mutual friction force that couples the two fluids. And we'll present some statistics of the mutual friction force and correlated terms, and a particular look will be done for the energy exchange and the mechanism between each fluid component. So we'll develop transport equation for the normal fluid, for the superfluid, and we'll see how they exchange this and that. And disentanglement of the inner energy exchange will open that box and to look who exchanges what with the other component and how things happen. We look at the scaling laws, if any, as I have mentioned earlier, and the related issues. To do that, we'll develop transport equation for the second order structure function that will depend on the third order, and transport equation for the third order moment that will depend on the fourth order moment, and that will help us to have a look at the what is more or less called in this community flatness factor. And the small scale intermittency will look at this flatness, but at the smallest scale, so we have the flatness of the derivative. A few words on the numerical simulations. Is a three-dimensional HVBK solver, so the equations you have seen before. homogeneous isotropic turbulence, the development of a spectral method, large eddy forcing, so for the two fluids we have a forcing. And that's two-fluid HVBK model, so the equations were mentioned before, and with the simplest possible force, as Emmanuel showed before. The values of the constant B is 1.5 invariant to the temperature. As I have mentioned, the ratios of the densities normal to superfluid will be considered 10, 1, 0.1, so a lot of normal fluid above T lambda, half, a little bit below T lambda, and a lower temperature with respect to T lambda is a lot of superfluid, a little bit of normal fluid. The external forcing will be considered for the two fluids at the same energy injection rate, so for the superfluid and the normal fluid will give the same epsilon star that has some value that can be found in the paper. A few words on the turbulence parameters. So the large scales are invariant with temperature. The small scales are with temperature dependent. So for these three ratios, rho n divided by rho s, 10, 1, 0, 1, the characteristics of the normal fluid here and of the superfluid here. I will show two things. The resolution, so delta is the resolution scale, eta is the Kolmogorov scale as computed for each fluid with its own viscosity, etc. So we see that the normal fluid is well resolved. We are at the level of the Kolmogorov scale. And here, the superfluid, we have the lowest ratio is 0.3, so we are more or less at 3 times Kolmogorov scale as computed with that viscosity. The other thing that we look at is the dissipation over the energy injected. So if we write what we call 1-point energy budget, we should obtain that the energy injected in the system equal to the energy dissipated by the system. But now, because we have two things that communicate together, what we'll obtain for the normal fluid is that it dissipates, for instance, at this high temperature, it dissipates more than it received. And the difference is, of course, this phi that is called the flux that will be exchanged between the two fluids. So what happened here may be reproduced by this picture. So the superfluid and the normal fluid receive the same epsilon star, but because of this flux exchange between the two, that the normal fluid will dissipate the quantity of energy that was received plus what it is received for the superfluid. And on the other side, the superfluid will dissipate much less because it transmits on that. Same messages from Emmanuel that this exchange actually will help the superfluid. They will ask less things to be dissipated, and that the normal fluid is in charge to dissipate, and that will be communicated by this energy transfer through the mutual friction force. What it should be seen is that we close this one point energy budget. It signifies that this column minus this column should be equal to 1 each time. What we see that is more or less the case. So it is one of the tests that we did, that numerical simulations are sufficiently well performed, so we have a good resolution to close at least the 1 point energy budget. For the superfluid, we should see this minus this. So here the sum of the absolute values should be equal to 1. So again, we see that that is the case. But with this message that the energy is transferred from the superfluid to the normal fluid. A few words on the energy spectrum for different cases. So a lot of normal fluid, equal parts, and a lot of superfluid. We see that a minus 5/3 is more developed for that, for the superfluid. Here, with all the discussion that we have put in the paper and association with the Reynolds number that can be computed for these temperatures. The inertial range extends for both the normal fluid and the superfluid, and when the temperature decreases, the Kolmogorov scale will decrease in a monotonic way, at least for our simulations. That's my only slide on beautiful pictures, but what is showed Here is the snapshot of isocontour of the vorticity of the superfluid that appeared in the mutual friction force. And then here we have the picture for the normal fluid and for the superfluid. And that's the energy exchange through the mutual friction force. And what we see is that the normal fluid will receive a lot of energy, and the superfluid will leave, will leave a lot of energy. And that happens in more or less, we see that with the eyes, but it can be shown in detail, more or less in the same places where we have rotational regions, so where we have vorticity of the superfluids. Some statistics of the mutual friction. The mutual friction was the product of the vorticity and the difference of the velocity. And we see that the energy exchange through the mutual friction, so there's a lot of positive values, that energy will be received by the normal fluid and energy will be given, provided by the superfluid. So again, the same message, but it is emphasized through the shapes of the PDF of the energy exchange. And the PDF of the energy exchange, that is represented here. So we see exponential tails, and that is associated with the exponential tail of the entropy of the superfluid, and also the value, dissymmetric value of the magnitude of the relative velocity. So contributions from the two terms are here. We go now to the transport equations. So the scale-by-scale energy budget, again, Emmanuel and I believe other people presented that. We start from the Navier-Stokes equations. We have now, we are in the situation that is the simplest possible because it is homogeneous isotropic turbulence. So some terms like the diffusion, etc., that will be removed. And we subtract the Navier-Stokes equation at one point from the Navier-Stokes equation at the other point. So again, the transport equation that we have had before. We multiply by that increment, so we obtain the time derivative or the transport equation of the second order moment. So that will be this moment. We do that for the normal fluid and the superfluid. So the index N and S will be mentioned each time. And what appears is the third order moment, that with a sign minus should be positive in the case of a direct cascade. We have a viscous term here. So depending on the viscosity of the normal fluid, the viscosity of the superfluid, and the term that Emmanuel showed 1 hour before, that will be proportional to the dissipation rate of the normal fluid and the superfluid. But it's not the energy injected, it is the dissipation rate here. And with a factor of 4/3, that is because we wrote this transport equation for all velocity components. So that is the total kinetic energy, which is a scalar. And this is why we have the analogy with the transport equation for the second order moment of a scalar that is known as the Yaglom equation. So the 4/3. If we did that for the velocity field one component only, and with a slightly different computation, but on the same physical basis, then we would have had the 4/5 law that is widely known in all communities, I believe. So the message is that the energy transferred through velocity fluctuations will leave together with other effects through the viscosity that, as I will show, will appear only at small scales, and effects, these are large scale terms, that in our case we only have two effects. This is the forcing, because we have the large-scale forcing here. And the other term is, of course, what we are interested in is the mutual friction form. So only two components that will contribute to this large-scale term. So in total, we have 1, 2, 3, 4, 5 terms for each equation. And we look at how all these terms live together. I only show results for two cases. So the high temperatures, in which we have a lot of normal fluid, and the other case in which we have a lot of superfluid. So at left we have the results for the normal fluid, and at right for the superfluid in red. We normalize this with respect to 4/3 epsilon r. So when we have a plateau of 1, that signifies that the sum of all these terms equal to 1 at the right. And what we see is that the viscous term here will be present at small scales and will diminish at larger and larger scales. This is the energy transfer through turbulent fluctuations, which is all this term. We do not have really a plateau, which signifies that the Reynolds number is relatively low and it is smaller than 100 here. This is the term that is associated to the forcing. We see that it appears at very large scales and it's smaller and smaller at smaller scales. And the forcing associated to the mutual friction force is all this term. So we see that it is important for large scales, it is important for intermediate scales, and it diminishes at small scales. But for this case, this contribution is much smaller than the contribution of the energy transferred through the cascade. This is a classical, I was not surprised to see this first result, because at this Reynolds number it is actually what happens. For the superfluid now, when we normalize with respect to the dissipation of the superfluid, that remember it is very small with respect to the energy injected, what we see that again we made sure that the sum of all terms is equal to 1 or whatever the normalization. But what we see that the energy injected here will be translated to the mutual friction force that will create a cascade. So we see that both of them will be equal over some range of scale here, but the level of that plateau is much higher than that of the ensured by the energy dissipation. So that signifies that here we create a cascade, we inject energy, we create a cascade, but that will be only counterbalanced by the work of the mutual friction force. So it was said before, but for other tools, that the mutual friction force actually plays a role of a dissipation, except it is not a viscous dissipation, it is take away energy through somebody else that will be able to dissipate. At a very much smaller temperature, so we have a lot of superfluids and a little bit of normal fluid. What we see that is the normal fluid, which is in a very small quantity, this time its own cascade is very reduced. We have the plateau that is much smaller than the value of 1, and all the work is done by the mutual friction force here. And for the superfluid, what we should have is that the energy transferred through the turbulent fluctuations plus the forcing and minus the work that is done by the mutual friction force should be equal to 1. So we see that a lot of energy is ensured actually by this mutual friction force that the effect of a mutual friction force that ensures the link between the two of them. We'll go next to the link between the third order and fourth order moments. And this is a transport equation that can be developed once again for the normal fluid and the superfluid. D111 is nothing else, this is a different notation, but it is nothing else than the third order moment, and this is the fourth order moment. In this equation, again developed for the homogeneous isotropic turbulence, we have a mixed fourth order moment that is delta U squared, delta V squared. At right hand side, so all these terms are what we call advection, so it's the transport of fourth order moment and mixed fourth order moment. And right hand side we have the term T111 that is related to the pressure, so delta increments of pressure gradients, and multiply by delta U square. I did not mention that the way to do that, it was Hill that developed that in 20 years ago, and the numerical results with DNS at that time, it was published in Hill and Boratov more than 10 years ago. The Navier-Stokes equations for the increments, it was multiplied by delta U squared to obtain all that, and there are mathematical manipulations. So this is the term related to pressure gradients, and we have two viscous terms. One of them is will really appear at small scales. It is that it's related to the Laplacian of third order moments, and we have another term related to the viscosity that is called and we at least in some communities, we call that a mixed dissipation term. We'll see that this term, unlike the others, will be present over large scales as well. So this is related to the viscosity. This will be the term related to the mutual friction force, so it's just multiplied by the delta U square, and of course what is related to the forcing. We look what happens now for the two cases. So the ratio of normal fluid, density of the normal fluid to the superfluid 0.9, almost 1, so a lot of normal fluid, high temperatures. This is for the normal fluid, this is for the superfluid. I kept the same order. And what we see, that is the sum of all this transport term. But when we compute the difference between this term and the pressure term, that will have this red term that should be compared to the black term. This is exactly the result that was obtained in classical turbulence, so published in that paper by Hill and Boratav. The conclusion was that all terms that are forcing, viscosity, etc., are much smaller. You see here more than 1 order of magnitude than all the other terms. So the conclusion was that we are in a stationary turbulence, so this term is equal to 0, but the advection terms equal to the work done by pressure gradients. So we have here in Navier-Stokes-like transport equation exactly the same result. If we look now at all the other terms, the viscous term, this one will be this one. So it is, of course, important at small scales, and it equal this dissipation source term that is here. And our mutual friction term is the magenta one here, that we see that it is much smaller for the normal fluid than all the other effects at this for this Reynolds number and for this case. Some things are similar for the superfluid, but we see that the advection term equal to the work done by the pressure. So the red curve goes over the black curve. Again, the mutual friction term will be much smaller, but however, it is more important than all the other effects. So it comes into play, and it should be accounted. And another thing that I did not say is that here we represent the absolute value of some terms, but this mutual friction term for the normal fluid is negative. So it will act as a dissipative-like term, where this one is positive, so it will be the same on the same size as the dissipation term. When we go to much lower temperatures, so we have a little bit of normal fluid and a lot of superfluid, we see that the conclusion is more or less the same, but all the other terms, so the dissipation source term and the mutual friction term, are, however, 15% of all the other terms, so that cannot be neglected. And for the superfluid, they are more or less comparable, but they stay a little bit less important. Some statistics of the intermittency of small scales. For the 3 temperatures here, the PDF of the gradients for the longitudinal velocity, normal fluid and the superfluid, and this will result into the values of the flatness of the derivative for different temperatures. So we agree with the literature, and we agree with the results of this flatness as a function of the Reynolds number in classical turbulence. We used the results from Japanese people, Ishihara, etc. And with error bars, etc. Superfluid in red, normal fluid in blue, and in black we have the total fluid. So we see that we have an increase, so high temperatures, smaller temperatures, and when we go towards smaller and smaller temperature with a resolution that we had at the beginning of 512 cube, we had a decrease of this flatness or diminishing of intermittency for the superfluid, but with a better resolution, 1024, and even better that we have things that are more or less comparable. So intermittency increases, not so high. The flatness factor is more than 6, maybe but smaller than 6.5. So it increases, but it stays reasonable and again in agreement with the classical turbulence. We have provided a picture of the energy exchange. So the mutual friction exchanges momentum between the two fluid components. It will take energy from the superfluid and will give work to the normal fluid. It will diminish the cascade of the superfluid. It will enhance the cascade of the superfluid. For the regions, when we show that it occurs in the regions with the strongest vorticity, it can be shown also through the correlation, etc. With the help of the scale-by-scale energy budget, so which was the second order related to the third order, the mutual friction term has a very important impact on the energy balance. We showed that on the one point, and of course that is translated to what happens at each scales. We did not, at this Reynolds number, we did not really, did not see a real inertial range. So we speak of a restricted scaling range. We did not extract, or we did it, but they are not really relevant, the zeta p and etc. So to discuss things as previously discussed. The local dissipation rate will be balanced by both the large eddy energy injection, but also the energy that is exchanged between the two fluids through the mutual friction force. As far as the higher order moments, the mutual friction shows no effect on internal intermittency, at least with this tool, across the restrictive scaling range or inertial range. And the energy source term, due to the mutual friction, is modified the small scale intermittency. It's something that I have chosen not to present here. That is, the development is presented in that paper, and the idea is to consider the very small scale limits of the transport equations that I've shown here, and by considering the R cube terms of this term, that we obtain equations of the derivative of this third order moment that will be related to the fourth order moment of the derivatives, etc. So we see which are the effects. And the mutual friction force that does not play an important role here, that will play a relatively important role for that. I think I have extracted some things that I wanted to show. It is mutual friction force does play a role, not so spectacular as I would have expected, and there are many things that are similar to classical turbulence. Now, our aim was to use tools that are usually used in classical turbulence and to apply that to these transport equations, which are similar to Navier-Stokes like they are Navier-Stokes like equations, including a viscosity for the superfluid that we have chosen here 10 times smaller. That is the role of the mutual friction, and of course a lot of work is ongoing. Thank you very much. I have no idea on
So from your first conclusion that the mutual friction mainly takes energy from the superfluid and puts it into the normal fluid, it would seem that you don't need any arbitrary viscosity in the superfluid equation. At least in the regime where you're working. Is it correct?
Yeah, we still needed it, but that is because of numerical artifacts. If you do not do it, that the energy will have a thermalization and etc. The energy, just the spectra, instead of decreasing, they have energy that grows at high wave numbers.
Okay.
But once again, here I showed the results with the ratio of viscosities of 10. We did it also for a ratio of viscosity 4 times smaller. And of course, the results per se change a little bit, but the message was exactly the same.
Since the normal and superfluids are nearly locked at large scale, it is tempting to describe them with a unique velocity field. Now, if you want to precisely describe this, the dynamics of this unique velocity field, you would put some the normal fluid viscosity in it, and it's tempting to put a viscosity which accounts for mutual friction dissipation.
Yes.
But it will not be a viscous term with second order derivative of velocity. Yes. Do you have some feeling of what could be the shape, analytical shape of a dissipative term which produces some transfer of energy which mimics the mutual friction dissipation?
Oh, it should inherit, I'm thinking at the same time, but it should inherit something from this mutual friction force. So we should have some vorticity of the superfluid and increments of velocity inside. But it should be... when we started this study, it was the opposite way. I mean, people usually, and especially experimentalists, showed the results for spectra and structure functions, etc., for the whole velocity field because they could not measure each of them. And when DNS came into play, but it's not a criticism, and we need all of that. And when the DNS came into play, then people showed what happens for this and for that, but we needed at this point to go to relatively simple model, and we received all the criticism for referee number 2 and referee number 3. That it is a model, we answered it is in the title, that it is a 2-fluid model, and we work on whatever will be a 3-fluid model in which we should couple with some other transport equation. But we know how to do that because it will be like in LES. Large scales do some like that, a small scale we have another. And we wanted to go to the behavior of each fluid to understand into detail. It's like a box, Pandora box, open to look how exchanges. And I come back to your question. The aim would be to go back to something that is a global fluid, but with this knowledge in mind, and to model the interaction between two of them, like a viscosity. Viscosity term is a distraction term.
Yeah, so this is a more pedagogical question. In your first or second slide, you had an equation for the mutual friction. I'd like to know how it was motivated.
The beginning, you mean?
Yeah, I think it was the first or second slide, something like that.
That was the talk of Emmanuel and other talks, I think. The expression of the mutual friction. Yes, this is the simplest model that...
I think there was one in the earlier one, in an earlier slide. Yeah, that one.
That?
Yeah.
That comes for all these people. And we only considered the first term.
Okay.
I think the notations are slightly different, but yeah.
I think Luca is not here, so it's dangerous speaking for him.
Sorry, Luca?
Luca in his talk tomorrow.
Oh.
Maybe as part of his talk, he's covering pedagogically an introduction to mutual friction.
If you look at, I speak again of our Journal of Fluid Mechanics paper, it is a very long introduction with all approximations that are done, different expression for the mutual friction force, and the choice that we have made is the simplest possible one, because as I have mentioned, the aim was to apply simple tools to understand how the two fluids discuss among them, and then possibly go to more complex models.
Yeah, maybe tomorrow there'll be a talk, if not. Any more questions, comments? If not, let's thank Luminita again.
Thank you. What we will do is that I will open the other presentation, and we'll see. And does it work the same way? Okay. A few words on the physical review fluids. I have several slides, but we'll see if necessary continue the discussion in the afternoon during or after Lorette, but at least we'll start. A physical review fluids, that is a new journal. New signifies more than 5 years now, but new with respect to other journals that are much older. So it is a journal that is at the context of APS, American Physics Society. It is a family of all physical review journals. And this journal has been created during 2016. So the lead editors are Beverly McKean, now at Stanford, Eric Lauga at the University of Cambridge. We have a journal manager who is Brad Rubin, so he takes care of everything in the journal. And these are the slides of a presentation that webinar that we have done for all people. A few months ago, it was still in 2022, so we were 2 associate editors, Roberto Zenit from Brown University and myself. But all the editors are here. So you come again, the lead editors. We have the letters editors, Guido Boffetta and Howard Stone, and all the other associate editors, so you might probably know some of them. The object of the journal is fundamental research in fluid mechanics. And the history of the journal, it was created in 2016 when the former editors of Physics of Fluids, who were young people will not know them, Gary Leal and John Kim, now retired. They decided to leave that journal, the Physics of Fluids, because it became AIP, American Institute of Physics. And they left for American Physical Society. And it is, I don't know if it is an official part of the story, but the reason was because it was much more expensive. So they said, okay, we leave away and we leave at the APS and we'll create a new journal. So they created Physical Review Fluids. Then Physics of Fluids stayed there, and they have a lot of success, but they continued on the basis of what former editors created. So now we go back to our journal. So it is devoted exclusively to fluid mechanics. Has grown rapidly. With we have statistics, you know, we have to wait some time to have statistics. So 574 research papers in 21, more or less this, or 22 now is more or less finished with that. And we have recently, a few years ago, but not at the beginning, we have introduced the Physical Review Fluids letters, which are shorter letter style papers that continues timely and important new results. So in 22 we had 43 such letters. And each month the editors select 2 to 5 papers for editor suggestion of particular interest, importance or clarity. I should say sometimes we select papers and then some other people decide afterwards, so I don't know how things happen exactly, but we have editor suggestion. The themes and the topics that we published are all these, that we see that turbulence is one of, if it's not the most important, the keywords that appears the most frequently. Flow instability, interfacial flows, boundary layers, etc., etc. So these are the word cloud of topics that appeared in these papers between all these years. A few words on the link with the division of fluid dynamics, that is a part of the APS. And for those of you who attend the GFD meeting at the end of November, that might know. And in that context, for that meeting, we have a gallery of fluid motion, and people propose movies, etc., from experiments or DNS, etc. And there is a competition, and there are winners. So the winners are invited to present papers and poster or video on the physical review fluids. We also have the François Frenkiel Award that is given for a paper judged to be the best in the previous year published in our journal, and for relatively young people, so the academic degree, the PhD, no more than 12 years ago. And I am sure people here, you had it. Yes, Georgia, 19 was that? 19 something? 18 maybe, but it was in, well, I remember 19 because it came a little bit or 18 maybe, yes, yeah, you know better. Yeah, so Giorgio had that François Frenkel award for one paper with Villois, and a follow-up of the link with the DFD. So after the during the Congress of DFD, we usually organize Fluids Next symposia. So for instance, we organized with Bruce Sutherland. It was in Phoenix, so 2 years ago. Fluids Next symposia, which was devoted to the climate change and the role of the turbulence in the climate change and modeling the climate, etc. But there are different topics. So for last year, for instance, in 22, we had a mini symposium, fluid mechanics in microplastics transport, and a focus session, a soft body slamming fluids, etc. So different, they can be members of the editorial board that might organize that. And some people, actually almost invite all of them, but they are invited to submit paper based on their talk. Few words, and that can go very fast. The criteria of publication in physical review fluids, it should be new research, not previously published, scientifically sound, so correct, and not misleading. Should significantly advance the physics of the flows and important in that field, and it should be as well accessible to readers. Now I work for it's the 5th year that I work as an associate editor of that, and I saw a very good paper from very good people, etc. We never give names, but they were simply not correctly written. So we asked the authors to make an effort and to explain, because the paper, it is devoted for the people to read them. So we kindly asked to explain a little bit more and not say it is obvious that, and it is obvious that it is 10 pages of calculations. How is the peer review process? I'll go very fast. It's only for the young students. After the manuscript submission, we might have an editorial. We call that upfront rejection, editorial rejection, if the editor considers that the paper is not appropriate for the journal, or sometimes is really a torchon. It's not good for anything. So we just we say it's not appropriate for the journal, but actually. Yeah, so it goes to the referees. We try to do that as fast as we can. And then based on this review, we have a first editorial deliberation, is either reject or accept, or we continue the process. We ask the authors to take into account, and most of us, we go into that revision process. And that goes back to the authors for the revision. It comes back to the editor. Again, it can be rejected or accepted, or it might go back to the reviewers, and we are allowed to do that twice, not more. If it's sometimes still ask for that point and that comma and that equation, that we should take a decision. So final editorial deliberation. The structure of a scientific paper, I will not spend a lot of time because that is common to all journals. What should you do in the introduction? Need for the work, put study into the context of a state of the art, the previous work, lays out the structure of the paper, tell the materials and the methods, and then in the results and the discussions that you should emphasize the findings, accompanying with an interpretation what was new that was found. And in conclusion, we should go back to what was important and put back into the context and explain what was the advancing from that paper. Oh, did I preparing a paper? It's okay. Before writing your paper, you should identify, well, now we speak of physical review family, but of course you should correctly identify which journal you target and look at the keywords and how things develop. We also have, somebody asked us, or among the questions, some papers are rejected from physical review letters. And because for instance, the reviewers said that it is a good subject, a good paper, etc., but this and that point should be developed, so that goes beyond the 4 pages of PRL, so it should go in another specialized journal, and this is why sometimes we get some of the papers that come to physical review fluids, but it is the choice of the authors, of course. It is a proposal that it is accepted or not. So when we receive papers for physical review letters, for instance, then those papers may go for the review, or sometimes they are only read by the editor, and on the basis of the previous reports, if we have previous reports, then it can be accepted or rejected. And sometimes we ask for more this and that. Write a cover letter. This is also the same thing for all journals. In the cover letter, you should at least say, hello, dear, this is a paper, and we submit because we found this and that in a few lines. Okay, when resubmitting, so after the reviewer's reports, you should answer seriously and not something like I have seen, oh, it is obvious that the reviewers did not understand, the reviewers are stupid, etc. So be factual and collegial. Address all criticism and do not assume and address referees or editors as being stupid. We have not received direct bad words, but we have been told that referee number 2 is really a stupid person. And we do not accept that. I mean, it should happen in a collegial, malicious or biased or etc. Even that you are allowed, of course, to propose referees, and also in the cover letter at the beginning, and also to say, I do not want this and that person because conflict of interest, and we do not ask why. And we respect that. Then we take into account that opinion. Oh, yeah. Oh, I mean, yeah, okay. You mean 2-line reviews? No. Yeah, I agree. You do not take into account this, but I never had. I speak of on the basis of my. Sorry, it is? I speak of myself. Oh, these are the slides that are made by Beverly and Eric. I am allowed to present. I was encouraged to present. I did not, at the beginning, I did not think of. But as I was told at the end of each presentation that we make in congresses, etc., to put one slide to advertise on the journal, because it is not yet, because of those reasons, it is not yet. I know many of you publish and many of you review, and I thank you very much for that, for both submission and reviewing, and at least 60% of people here. But I speak on the basis of my experience. I did not have maybe other people. Okay. No, we have so these words were made by the lead editors who are supposed to see more or less all papers. I only see mine, but on the basis of that I have seen for more than 5 years now, people stay correct. So it's not, and we try, at least I try when I have been told I do not wish that referee. I mean, we have plenty of others. It's not, sometimes it would be interesting to have the viewpoint of that referee, but if you have... Yes. What should we do if we feel? Just use other words. Dear. Yeah. But. Yeah. Just try that. Yeah. We do not. Yeah, and I can tell you that most of the people do not agree. Many. They do not agree. Just find a good... Yeah. Yeah. And sometimes I have seen also the following situation. Oh, this referee is stupid, blah, blah, blah. You should contact... this referee. But that referee was exactly that referee, that I'm not allowed to tell you that it is that. Oh no, please contact my friend because my friend agrees with me and I'm sure. And I should tell you that as before doing this work, I thought, I speak of the turbulence community that I know better, but I thought person A is friend with person B, and they are friends with person C, etc. After this, I understood that person A, yes, person A is not at all the friend of person B, even if they take the coffee together. And they do not agree, and they take the opportunity to be anonymous, to say this is the worst thing that I ever... so what we try to tell you is not to choose your words to say, and I think, is the work. This is how to write a referee report, but with the same message to tell, we try to help the authors how to improve the, of course sometimes there is no way, but when it's a possibility to help the paper to, and so you should understand that also for the young students that the aim of the referees and the work we are asked to do is not to bother you, it is to improve the paper that will be published later with your name. So that's the aim, is not to bother you and to ask you to... be mindful of the time that the authors are waiting, so this is for the referees that are more than... we are reminded each Saturday morning that papers which are under review for more than 60 days that you should do something, etc. So you usually give 1 month. You can go a little bit beyond, but 2 months it starts to be too long. And I think if you have no time to referee, just tell it. We understand. But tell it immediately so we can look for somebody else. And that was an invitation to join, but as I said, I know at least 60% of the people here are already in the authors and referees pool. And I thank you for that, but you can join that to become a referee. And I think, yes, that we have a new journal club that comes from time to time on some paper that is invited to be developed in the journal club. It is taken into account to what? Yes. Yes. We try to take into account, but sometimes that is the referee database. I speak of this journal, I don't know for the others. So when you go to those referees, then we see if they are reviewing another paper for physical review, all of them. We see that they have a task, so we try not to ask too many things. So sometimes the referees that you suggest that help us, but sometimes, and if really we need that person opinion, that we write a direct email very kindly that I really need your opinion on this, on that paper, and then usually people do that. Otherwise, we work with tasks. I mean, we indicate the referees, and then the journal staff knows that they should contact those referees. So we try to do, but sometimes it is not the case. So if you say that, again, I speak of me, this time I try to take into account, oh, you should not have a list like that. I mean, if you mention one person or two, we try... So he looks, how should I have troubles with physical review fluids? I can tell you what it is when we open your page. There are some keywords, for instance, your page, the page of anybody. There are keywords, but they were put there by the first editor who looked for you as a referee. But other people can add things. And usually we do not remove because, I mean, once you know superfluids, then you know superfluids. But we may add things. And the email where we can contact, and we see the papers that you reviewed for us. So we do not know that somebody asked me if we know, we definitely don't have access to some other database. So if you review for Journal of Fluid Mechanics or, I don't know, 10 other reviews that we don't know. It's only our... We can see that, yes. It is done automatically. For the authors, yes, we can have that. No. But that's a physical review in general, not only us. Sorry? Yes, I finished. But if you have questions... So you are very welcome to submit papers. Yes.
Yep.
Yeah, he has a question, Victor.
Is it open access or how does
it is not open access, but it is how does that? I don't take care of that. Some of them are open access.
Hybrid.
Hybrid, yes, yes. Okay. Some of them are open access. It is not open access. Yeah.
In addition, physical review has very liberal policies about posting articles on the university website, your own website, and so on. So take advantage of that. Everybody should be posting their articles on their websites if they want to be found.
And the embargo, it's you sign for 12 months, but in Europe it's 6 months. So if Americans will impose you a 12 months delay to publish your final paper, web page, it's only 6 months. It's European regulation, which prevails the American one. Now we'll continue, but
thank you very much.
Thank you.